Just a couple of remarks on energy in strings. So, when there is a transverse wave that is propagating through a string, a transverse wave propagating through a string, say, so the wave was traveling along the x-axis. That means the string was placed along the x-axis. The particles of the string were in their mean positions, lying along the x-axis originally, right? There was a disturbance produced in the string. There was a disturbance produced in the string, and the string assumed a certain shape. Say the string assumed a certain shape, right? After a while, at a certain instant of time, it had a certain shape. So obviously, this is a snapshot view of the wave. This is a snapshot view of the wave. Realize that, say, so these are particles of the string. These are particles of the string now lying like this, right? Do you realize this part of the string is in a stretched state, Why? Because, see, the shaded portion was originally along this. This shaded portion was originally along this, right? And now, so this was the normal state, the normal length of a certain segment of a string. When the string assumed this shape, this becomes the revised length of the string. That means the string is stretched. So now there is potential energy associated with the stretching of the string, which is called the elastic potential energy of the string, which is elastic potential energy of the medium. Elastic potential energy of the medium, which is the string. Now the question is, what is the elastic potential energy associated in this part, right? So this portion is located at x and has a length dx. This portion is at x and has a length, original length is dx, right? When the string becomes stretched, or rather assumes this shape, when the wave is propagating, when the disturbance is propagating, after a while, this becomes the length of the string, dl. This becomes the length of the string, dl. Right? dl is more than dx. The string is stretched. It's stretched. There is potential energy associated with the string, right? And this is dx, and this vertical length is dy. This vertical length is dy, and this, like I said, is dx. Clear? Now, let's focus on this dl. There is tension in the string. Right? So if I focus on this dl, if I look at this dl separately, then say at this instant of time, the tension in the string is T. This is the length dl. Alright? There is work done by T. That's why dx changes to dl. Right? And the work done by tension is stored as potential energy in the string. The work done by tension would be the potential energy of this element dl, right? So what's the work done by the string? T into dl minus dx. Yes or no? Do you realize? T into dl minus dx is the work done by tension. See, tension is always acting along the length of the string, right? So it's T, because of which the string is stretching, right? How much has it got displaced? dl minus dx. Its original length was dx. Now its length has become dl. So what is the stretching along the tensile portion? dl minus dx. dl minus dx is the stretching that has occurred, right? So this is the work done by T, and that must be the potential energy of this portion dx. This must be the potential energy du of this portion dx. Yes or no? Now, realize from Pythagoras theorem, can I say dl is root dx squared plus dy squared? Can I say this? Then dl dx is going to be root 1 plus dy dx whole square. dl dx would be root 1 plus dy dx whole square, right? dy dx is what? The slope of the tangent at this point where the element is located. At a given instant of time, this is dy dx, the slope of the tangent where dl is located, right? Now this I could have written as t dx into dl dx minus 1 into dl dx minus 1. This is t into dx into, this is root 1 plus dy dx whole squared minus 1. Now, for small oscillations of the string, I will assume that the string remains very flat. The string remains flattish. So if the string remains flattish, what it really means is that if this is my dl and if I draw a tangent and this is my x-axis, if this is my dl, this is the tangent, and if this is theta, then I'll assume that this theta is small. If the string remains almost flattish all the time, not significantly, right, we'll assume that this theta remains small all the time for the string, right? That's the analysis that we are going to carry out. This is the slope of the tangent at the point P where the element dl is located. So tan theta is going to be dy dx at that instant of time, and dy dx at that instant of time is written as dou y dou x, So dou y dou x will be a small number, dy dx will be a small number. Now from binomial theorem, if a quantity a is numerically very small, then 1 plus a to the power n in general can be approximated to 1 plus na. If a is numerically very small. Now that's exactly what I'm going to do. This is like t into dx. See, this is 1 plus dy dx, which is like dou y dou x essentially, so might as well start to write dou y dou x because it's at a given instant of time, to power half minus 1, right? So dou y dou x is very small. We are assuming that tan theta is very small, theta is very small. We'll assume at all times. And so this is 1 plus a is dou y dou x whole square, whole to power n. Since this is very small, this can be written as approximately 1 plus half into dou y dou x whole square. 1 plus half into dou y dou x whole square. This is approximately t dx into 1 plus half. I start to write dou y dou x whole squared minus 1, right? That's the potential energy of this chosen element. That's the potential energy of this chosen element. Clear? Is that okay or not okay? So the potential energy of this chosen element is T dx into half dou y dou x whole square. That's the potential energy of a small element, originally dx, now turned dl, right? Dou y dou x is the slope of the string at x, slope of the string at x, tan theta, right? Now du dx, rate of change of potential energy with x along the string. Du dx, as you can see, is half of t into dou y dou x whole square. That's rate of change of potential energy with x. Hey, if v is the wave velocity, right, and vp is the velocity of this particle, vp is the velocity of this particle, v is the wave velocity, then did I not tell you vp, particle velocity, would be minus v dou y dou x? Remember this? vp is minus v dou y dou x. Recall this result? Dou y dou x is the slope of the tangent at p, that is at x. So dou y dou x whole squared can be written as vp squared by v squared, vp squared by v squared. V is the wave velocity along the string, v is the wave velocity along the string. V squared, T is the tension in the string. And did I also tell you the velocity of transverse waves in a string is root T by mu. Mu is the mass per unit length. Mu is the mass per unit length, right? So very clearly T by v squared, as you can see, T by v squared is mu. Mu is the mass per unit length, right? So vp squared by v squared, T by v squared I replace by mu. So this is half of T into half of mu into vp squared. Right? Hey, what's the kinetic energy of this element? dk. The kinetic energy of this element is half mass of this element, mu dx, into vp square. That's the kinetic energy of this element. That's the kinetic energy of this element, right? Do you then see that dk dx is half, dk dx is half of mu vp square? Rate of change of kinetic energy with x, rate of change of kinetic energy with x of the string, right? So half of mu vp squared is also rate of change of kinetic energy with x. See? Isn't it? Yes or no? And so which means rate of change of potential energy with x is the same as rate of change of kinetic energy with x, and this expression is extremely important. This expression is extremely important. The total energy E would be potential plus kinetic, which is like, since kinetic is the same as potential, right? Du is the same as dk. Du is the same as dk. So let's say, so let me call dE, the total energy is for a given element is the total potential energy plus the total kinetic energy. Yes or no? Which means dE, the total energy, is twice du, because du is the same as dk. right? So dE dx, rate of change of total energy, would be twice du dx, where du dx we already know is half t dou y dou x whole square. Now, one thing that I want you to take cognizance of. If I just look at a particle, not the medium, right? The particle, every particle, let's say, is executing simple harmonic motion with this being the mean position. At the mean position, there is maximum kinetic energy, minimum potential energy. At the extreme position, the amplitude position, there is minimum kinetic energy and maximum potential energy. That's a particle view. But let's say when this wave is propagating, there is a medium view. Energy related to the medium rather than this, right? So when I talk of the energy related to the medium, so this is all energy in the medium because it's related to energy of the string, right? Now, what I want you to understand is very clearly, so originally, say the string was like this and this was an element of the string in its normal state. This is an element of the string in its normal state, right? So this element goes up and down executing simple harmonic motion. After a while, this element gets to its upper extreme. This element gets to its upper extreme. That means its amplitude position gets to its upper extreme, its amplitude position. Now, if you just look at the element, and this is elastic potential energy in the string. By the way, this potential energy is elastic potential energy in the string because of the stretching of the medium, because of the deformation of the medium, Now, if you look at this element, right, this is executing SHM and the shape of the string varies sinusoidally. So when this gets to its uppermost extreme, this element gets to its uppermost extreme, it's like this, tangential. The element will be tangential to the curve, right? And do you realize that there is no change in length of the element? There is no change in length of the element between its mean position and its upper extreme. There is no change in length of the element. That means if there is no change in the length of the element between this state and its upper extreme, while the wave is propagating, that means the potential energy, the potential energy here is minimum. Like it was in this, the potential energy is minimum. Here also potential energy is minimum. That means when this element reaches its upper state, uppermost extreme, its potential energy is minimum, so is its kinetic energy. In contrast to what a particle does, because its velocity is 0, when it reaches the upper extreme, if you look at this element, its potential energy becomes minimum because it's unstretched, and it has 0 velocity at the upper extreme, so its kinetic energy is also minimum. So I'm talking of energy of the medium now, right? I'm not focusing on the particle, I'm talking of the medium, right? Now, after a while, if you look at this, the string could have also assumed, say, this element, while the string does this element, the string could have assumed this position where the element is like this, where this element will be like this. This could be the shape of the string. Particle, don't talk of the particle, we are talking of the medium. Yes, potential energy is minimum. So we are now talking of the energy because of the deformation of the medium. This is energy because of the deformation of the medium. So that is different. So don't get confused with potential energy and kinetic energy of a simple harmonic oscillator. Alright, this is energy because of deformation of the medium. Understand that there is a distinction, difference. When the string attains this state, this particle, this element would be now like this. Instead of being like this, it will be like this, right? It has come to its mean position. The shape of the string looks like this. This is the shape of the string. And when it is like this, when this is the shape of the string, this element has maximum stretching in this state. This is the minimum stretching. This is also minimum stretching. When it goes this way, the element has maximum stretching. This element dx that you saw here, when the shape of the string becomes this element has maximum stretching. Maximum stretching. That means if it has maximum stretching, you would expect what? Maximum potential energy. Maximum potential energy in the state. But it has come to the mean position. So it will also have maximum kinetic energy. It will also have maximum kinetic energy. Maximum kinetic energy. That means in the mean state when it comes, you know, it has maximum kinetic energy. The medium has also maximum potential energy. That means the kinetic energy and potential energy functions are in phase with each other. Together they are reaching their minimum. Together they are reaching their maximum. This is what happens. Right? This is not the particle side of the story. This is the medium side of the story. This is the medium side of the story. Right? Take these results into account, and this du is half t dx dou y dou x whole squared, same as dk. All of this you should remember. Right?